Hello, good evening, kids. How are you?
Fine, ma'am.
Okay. Stephanie, today I thought to start Newton's law of motion since we have completed the uh, motion in a straight line. Let me post another message, Pute. Give me a minute. Great. Okay, Stephanie, don't worry. Your mic is not working. Okay, let me share my screen with you. Okay. Hope you can see my screen, isn't it? Okay. All right. Okay. What is happening here? When let's think like this. So when there is a object is moving, okay, it may slow down and eventually stop. If you throw a small white marble, there are small glass balls, marbles. If you throw this away, at some point it slow down and eventually stop. Because of why? Because there is a force called friction. Okay. So friction is a kind of a force that opposes motion. That opposes the motion. Means it acts in the opposite direction to the movement of the object. There is another lesson for the friction. I'll explain it later. But here, just assume like that. Friction is opposite to the direction of the movement of the object. Okay. So different surfaces can create different amounts of friction as well. Like rough surface produce more friction and that object can stop more quickly. And smooth surfaces produce less friction, allows object to move for a longer time. So but why? But Newton in his laws told if the object is moving, if the object is moving with the constant speed or the constant acceleration until another external force applies on that, or else object is stays still or stays in stationary position until another external force apply on it. Likewise, he has explained three laws to the physics. Actually, this lesson related to the physics in science area. In science there are different areas in biology, zoology, chemistry, physics. Likewise, so these methods or this lesson actually related to the what physics. Okay, let's watch a small video on this and try to understand.
What are Newton's three laws of motion? Sir Isaac Newton was a famous scientist that lived almost 400 years ago. He is famous for learning and understanding how and why objects move, like when an apple falls from a tree. Because he figured out why objects move, we call them Newton's three laws of motion. The first is called the law of inertia and explains why things move. It says that an object at rest stays at rest, and an object in motion stays in motion at its same speed and direction, unless acted upon by another force. So this ball just sitting in the grass won't start moving on its own, it'll just sit there at rest. But if I kick it, my foot would be applying a force to it, and the ball would move. Newton's second law talks about how objects change when a force acts on it. This law says the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Sounds pretty confusing, doesn't it? That just means the acceleration of an object, how quickly it starts moving or changes speed, depends on two things. First, how hard you push or pull, and second, how heavy the object is. This law tells us how force, mass, and acceleration are connected. The mathematical formula is written as F equals m times a. The force needed is equal to the mass of the object multiplied by the acceleration. So, if a rock weighs 10 kilograms and you accelerate it at 5 meters per second squared by throwing it, how much force is needed? If 10 kilograms is the mass and the acceleration is 5 meters per second squared, that is 10 times 5, which is 50. And because Sir Isaac figured out the laws of motion, we call the force a newton.
Indeed.
So the answer is 50 newtons of force. Which brings us to Newton's third law of motion. For every action, there is an equal and opposite reaction. Think of a swimmer moving through the water. To go, the swimmer pushes the water backward with their hands. That's the action. The water pushes them forward. That's the reaction. Or think of a rocket ship. It shoots out gases down. That's the action. And the gases push the rocket up. That's the reaction. The action and reaction is the force, and they are always equal in strength but go in exactly the opposite direction. And those are Sir Isaac Newton's 3 laws of motion. Number 1, things stay still or keep moving unless a force changes them. Number 2, the amount of force, mass, and acceleration are all connected. The math formula is F equals m times a. And remember, every action has an equal and opposite reaction.
I am going to replay this video, Pute. Please look at again.
What are Newton's 3 laws of motion? Sir Isaac Newton was a famous scientist that lived almost 400 years ago. He is famous for learning and understanding how and why objects move, like when an apple falls from a tree. Because he figured out why objects move, we call them Newton's 3 laws of motion. The first is called the law of inertia and explains why things move. It says that an object at rest stays at rest, and an object in motion stays in motion at its same speed and direction, unless acted upon by another force. So this ball just sitting in the grass won't start moving on its own, it'll just sit there at rest. But if I kick it, my foot would be applying a force to it, and the ball would move. Newton's second law talks about how objects change when a force acts on it. This law says the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Sounds pretty confusing, doesn't it? That just means the acceleration of an object, how quickly it starts moving or changes speed, depends on two things. First, how hard you push or pull, and second, how heavy the object is. This law tells us how force, mass, and acceleration are connected. The mathematical formula is written as F equals m times a. The force needed is equal to the mass of the object multiplied by the acceleration. So, if a rock weighs 10 kilograms and you accelerate it at 5 meters per second squared by throwing it, how much force is needed? If 10 kilograms is the mass and the acceleration is 5 meters per second squared, that is 10 times 5, which is 50. And because Sir Isaac figured out the laws of motion, we call the force a newton.
Indeed.
So the answer is 50 newtons of force. Which brings us to Newton's third law of motion. For every action, there is an equal and opposite reaction. Think of a swimmer moving through the water. To go, the swimmer pushes the water backward with their hands. That's the action. The water pushes them forward. That's the reaction. Or think of a rocket ship. It shoots out gases down. That's the action. And the gases push the rocket up. That's the reaction. The action and reaction is the force, and they are always equal in strength but go in exactly the opposite direction. And those are Sir Isaac Newton's 3 laws of motion. Number 1, things stay still or keep moving unless a force changes them. Number 2, the amount of force, mass, and acceleration are all connected. The math formula is F equals m times a. And remember, every action has an equal and opposite reaction.
Okay, that's the summary for the today's lesson. Let's continue. Okay, nature of force and its effects. So forces, when we talk about the forces, it's simply a push or a pull. For example, when we push a table, pull a rope, or lift a bag, so we applying a force. So if an object is at rest and we want to move it, what we have to do? We must apply a force in a direction we want to move. In a direction we want to move. Now, does an object move immediately when we apply force? Any experience? Like there is a huge heavy box. So does an object move immediately when we apply a force? Not always. Why? If we push table very gently, it may not move at first, but when we increase the force, okay? When we increase the force only, after some point, the table start moving. I highlight this thing. Increase the force. Increase the force. After some point, the table starts moving. Okay? Why is that? There is a friction in between that heavy box and the floor. When we apply the force that is exceeding the friction only, it starts moving. That's why I told you. Sorry, but we increase the force. After some point, the table start moving. So this shows that small force may not be enough to move an object, but a larger force can make it move. Okay. So what are the types of forces? Push or pull. But what is it mainly depends on? It mainly depends on the force we apply on the object. Okay, here it's a graphical representation of the same thing. Pushing a table, pulling a rope, or lifting a bag. These are the examples for applying applying a force. Okay. So what is the reason? Why doesn't it move at first? Here I explained it. The reason is it does not move at first is friction. Friction means there is a force applying between the object and the floor. It's actually opposed to the motion. Its friction opposes motion. So when force is small, friction can balance it. So that's why there is no movement. Here, friction can, if we apply small force, friction can balance it and there is no movement. What will happen if we start to apply more force or a larger force? Friction is overcome. Then the object starts to move. For example, one person cannot push. Here, one person cannot push a bus. But there are many people in the team. Yes, force become larger enough. Then bus started to move. Sorry. Here you can see the applied force in the direction we want to move. Friction is opposed to the motion. Here it apply large force. It represent with the big arrow. Big arrow. This is actually exceeding the frictional force. Then it started to push to the way we actually want to move. Then balanced versus unbalanced forces. What is that? Okay, balanced forces mean equal and opposite and net force is 0. Let me show it on the board. Sorry. Okay. balanced. Let's talk about balanced forces. And this side unbalanced. Okay, let's think about, sorry, let's think about there is a box on the floor. This is the floor. Okay, or a table. Assume we are going to apply a push force to move this into this direction. But what about friction? Friction is actually to this side with the flow. This is friction. Sorry. And this is the force we applied. Let's think we applied force as FA and frictional force as FF. F friction. Okay. FF is equals to FA. What will happen? Any idea? Equal forces acting opposite. Equal forces acting opposite. Equal forces are acting opposite. Which means the object can't move. Okay? Object does not move. Remember that. Object does not move. But if we, let's take the net force. Net force means F net. F net means FA minus F friction. Okay? FA minus F friction. FA means the force we applied. Force we applied. In Sinhala we call it as Shuddha Bale, Shuddha. The difference between the opposite sides, okay? FA this side, FF this side. Remember, force is what? What quantity? Scalar quantity or a vector quantity? Amasha, any idea? Force is a vector quantity. Okay? So that's why it has a direction with their magnitude. With its magnitude, it has the direction. It has a quantity and the direction as well. Minus F means the direction is opposite to the applied force. Okay? Now, F net is, in this case, we can say FA equals to FF. Frictional force is equals to the applied force. So what's happening to this expression now? F net equals FA minus FA, because frictional force is equals to the applied force, which means this is become 0. This is A. Yeah? This is become 0. So net force become 0. This is net force. Net force become 0. What about the unbalanced forces? Again, let me draw the same picture here. This is the surface or the table. And let me keep the same box on the surface. And frictional force is Fa. And applied force is, sorry, I did a mistake. Not FF, frictional force, FF. And applied force is capital FA. This time I don't take FA because previously FA equals FF. Ne? So I will take the value as FB this time. And FB is greater than FF. It is greater than the frictional force. So I will draw a big arrow here. This is greater than the previous FA. Now what will happen? This is FB is not equals to FA. Now the object is moving to the direction where the force applied. Force applied means the biggest force. Okay? Biggest force is this side. So the object is starting to move that side. Okay? What about the F net? Net frictional force. F net equals the force we applied minus the frictional force. But we know from here, sorry, F not FA, FB. This time we took at FB. FB is greater than FF. So F net also greater than 0. It shouldn't be 0, which means the object started to move. Hope you understood the difference between the balanced forces and unbalanced forces. You have to remember in the balanced forces, equal forces are acting opposite. An object does not move and net force become 0. And here, unbalanced forces, the object is moving to the direction where the force applied, and F net is greater than 0 and the object started to move. These are the differences between balanced forces and the unbalanced forces. Let me share a screenshot of this as well. Give me a minute. Better you can write this down, and to Stephanie, Amasha. Done, Pute? Okay, let me share my screen. Here you can see some examples. Book on a table. You know, there is a gravitational force applied on any kind of object on the earth. So that is balanced with the normal force applied by the table. That's why its book on the table is stays still. What happened in this kind of situation in a tug of war? Okay. So this rope will not move here to this side or this side. So it stays still. It does not move because this boy applied 50 Newton force and also this girl also applied 50 Newton force. This is not moving. This is stays still. So what about these unbalanced forces? Boy is pushing uh, this box with more force than the frictional force. You can see here the frictional force is 10 Newton, which is lesser than the applied force. It's the 30 Newton. But what is the net force? It's 30 minus 10. Net force is 20 Newton to the right. 20 Newton to the right. You can see the box start moving right. Because of this box starts moving right. Here you can see kicking a soccer ball. Okay. He applies 20 Newton kick. 25 Newton force to the right. So what is happening? Ball starts moving right. Okay. Important thing, balance forces cancelled out. You can remember on the board as well. Fa minus Ff, what happened? It becomes 0, which means no change in motion. Unbalanced forces do not cancel. Net force is not equals to 0, greater than 0. So it change in motion. It starts to move. Okay. Let's go to the next. Effect of smooth surfaces. What is happening? There are different kind of surfaces when we talk about the forces. So on a very smooth surface like ice, oily, for oily surfaces, okay, what will happen? Even a small force, we can move an object, which means we have to apply little force to move that object because frictional force is very low in this type of surfaces. This friction is very low and the forces become unbalanced and the object also move easily because we apply more force than the friction, then the object is easily move. You can see here there's a glass surface and the wood surface. Glass surface, you can see this trolley travels more distance sorry, than the sand gravel surface. It is rough. What about the wood surface? It's between the glass surface and the sand surface when we consider about the frictional force applied on this trolley. Okay. Uh, yes, these are the things. And force depends on direction. What is that? Direction of force. Force has a direction because remember force or Newton. It's a kind of a scalar quantity. I think I have explained it on unit 2 also. What is the scalar and vector quantity? Sorry. Okay. So if force is applied in the same direction, object speed up. Let's assume there is a trolley. This kid tries to pull it. And another, her friend is trying to push it. So which means both forces are applied into the same direction, which means object started to speed up. What will happen if we apply the force in opposite direction? Okay, it's hard to what push the trolley. And here the weight also a factor of this force. If samana F equals ma, okay, the weight also a factor of the force applied by this person. So F cart equals F person. This is opposite direction. So F cart doesn't want to move, but person want to move it. Okay. But it's due to this F cart or the frictional force, the person has to push this cart with more effort. So which means object slows down. Okay, that's the theory of force depends on direction. Then again I put this slide to remind what are the physical quantity and scalar quantity and the vector quantities. Remember, vector quantities have a magnitude with the direction, and scalar quantity only have the magnitude, no direction. Especially force is a vector quantity. Then force is a vector because force has magnitude and the direction. So force is a vector quantity. And the direction of a force is shown by a straight line called the line of action. Can you remember in the previous also I showed there is an arrow uh, on top of the force. Let me show you on the board. You have to show the direction. Huh? Like this. FA, if the force is applying to the right direction, you have to show it with the arrow. And this is applying to the left side. You have to draw the arrow to this side. Okay. Straight line called a line of action. So you have to show it using the arrow. Okay. So introduction to the Newton's law. And there are 3 laws. Newton's first law, Newton's second law, Newton's third law. The main reason I have pasted these images, Pute, it's easy for you to remember the images than the words. Look at this. Object is at rest or moving with the constant speed if someone until someone apply an external force. So that's the first law. What is the second law? It's F equals ma. The force on an object is equals to its mass times mass into its acceleration. That's the second law. Okay. And third law, what is it? For every action, there is an equal and opposite reaction. The rocket is, what the rocket is doing, it's try to push the air down. Air, that's the action. And air is try to push the rocket to the upward. What will happen? That's the reaction. So that is Newton's third law. Okay. So who introduced this? Sir Isaac Newton. Okay. Now let's talk about Newton's first law. Law of inertia. Why this law of inertia? Usually object doesn't like to change its movement. For example, if there is a book on the table, we have to push or apply that book with some force. But it should exceed with that frictional force. If we can exceed the frictional force only, it started to move. But at the beginning, it's hard. It's hard to push. But let's think about the object is moving. Let's assume a cricketer throw a ball or something. Once we stop, you can see sometimes cricketers also try to push away. Why that? With the ball, he is trying to push away. Because of this inertia, ball doesn't want to stop at once. Yeah, කැමති නෑ. Okay? අකමැත්ත is inertia. He dislike to stop. He dislike to even start sometimes. If it stays still, it doesn't want to move. That's why we have to apply force that is exceeding the frictional force. It's not easy. Even if the ball is moving, it doesn't want to stop. That's why that cricketer who catch the ball sometimes pushed away. Let's assume someone try to get down from the traveling bus or a train. After some time, he has to run and slow down. He has to slow down his body speed. Why? He dropped from the traveling bus or the moving bus, moving train, what will happen? He has to run for some time to stop his body speed. That's called inertia. අකමැත්තක් තියෙනවා පොඩ්ඩක් නවතින්න. Okay? That is inertia. Okay? But what is this Newton's first law is saying? Very simple. An object at rest stays at rest. An object in motion continues in motion unless acted upon by an unbalanced force. I told you, there is a book on the table. It is like to stay still. But if we apply the force, unbalanced force, which is exceeding the frictional force, it started to move. And what will happen? The moving ball. That cricketer tries to move it with a bigger force and try to stop it. Stop it with the opposite side. Okay, so unless upon by an unbalanced force, this property is called inertia. Okay, the tendency of an object to rest changes its motion. Object don't start, stop, or change direction by themselves. So these are inertia. Okay, first example is another kind of carom disc. Okay, it's move until the carom board apply frictional force. What is this? Inertia. Okay. Usually the people are also same. We don't want to change our position. Okay. The object at rest stays at rest. If you want to move it, we have to apply an external force. Newton's first law. Look at this. Watch this video. What do you think? Is that inertia of rest or inertia of motion? Bhute. Haven't I shared my screen with you?
Yeah.
No? Oh, yes.
No, ma'am, we can't see the video.
Ayo, sorry then. Let me. Okay. Sorry about that.
Good morning, Sandeep. Wake up.
Huh? Give me 5 more minutes.
Come on, Sandeep. Wake up. You have videos to shoot.
Hi, friends. I'm sure you felt lazy to get out of bed and start your day, right? But don't feel guilty about it because according to physics, all bodies feel lazy. In physics, the laziness of a body is called inertia, and that's going to be the topic of this video. Let's understand the concept of inertia with some simple examples. If you try pushing a big table, it's difficult to move it, right? We need to apply a very large force to move the table. Why is that? The table has a natural tendency to resist a change in its state. The table is at rest, it's stationary, so it wants to remain at rest. It's lazy, it doesn't want to move. This is called inertia of rest. Now if you consider the example of a moving ball, what do you need to do to stop it? You need to apply a force. As you saw here, I applied a force to stop the moving ball. Otherwise, it will keep on moving, right? Obviously, we are ignoring the air friction here. Another example is a rocket in space that wants to keep on moving. It does not want to stop. The ball and the rocket, they are lazy to change their state of motion. This is inertia of motion. Does everything have inertia? The answer is yes. So basically, everything is lazy. Now, do all the bodies have the same inertia? What do you think? The answer is no. So what does inertia depend on? Let's find out. Consider the example of a shopping cart and a train. Let's say both are at rest. Which one do you think has more inertia? Think which one will be more difficult to move. Obviously, it is more difficult to move the train as compared to the shopping cart, as the train is much more heavier than the shopping cart. So inertia depends on the mass of the body. Greater the mass, greater will be the inertia. In fact, we say that mass is a measure of the inertia of a body. And the same also applies if both the shopping cart and the train are moving. Let's say they are moving at the same speed. Which one do you think is more difficult to stop? The shopping cart or the train? Again, the answer is the train, right? You don't want to be standing in front of a moving train because it has greater mass. So it has greater inertia of motion. So remember, greater the mass, greater will be the inertia, whether you talk about inertia of rest or inertia of motion. Sir Isaac Newton first described the concept of inertia in his famous laws of motion. In his first law of motion, he stated that an object at rest will remain at rest and an object in motion will continue to move at a constant velocity unless acted upon by an external force. In other words, an object's tendency to resist a change in its state of motion is called inertia. And remember, as we discussed, greater the mass of the object, greater will be its inertia. That is why the first law is also known as the law of inertia. Are you ready to see a tablecloth magic that's based on this law of inertia? Here it is. Ready? 1, 2, 3. Did you like the magic trick? Luckily, I didn't drop any of the objects on the table. Now can you tell me, the objects on the table, were they in the inertia of rest or inertia of motion?
What is that? Anto. Is that inertia of rest or inertia of motion? Stephanie?
Inertia, Rest.
Yes. What about Amash and Stephanie? What is your answer?
The objects are in the inertia rest.
Inertia of rest. Stephanie, what about you? He can't. Oh, sorry. She can't speak, ne? Sorry. It's inertia of rest. Okay.
What do
Both
you
are
think?
correct, huh?
Do let me know your answers by putting it in the comments below. I'm looking forward to reading your answers. So next time you're feeling too lazy to get up and start your day, remember that it's just your body's natural tendency to resist change. But with a little push, you can overcome that inertia and accomplish great things. Now, if you consider the example of a moving ball, what do you need to do? What do you need to stop it? You need to apply a force. As you saw here, I applied to. So come on, leave your inertia of rest, move your hand and hit the like button and subscribe to our channel.
Okay. If you want to do that, hit the like button and subscribe. Okay. Let's continue lesson. Okay. What is Newton's first law? An object at rest stays at rest, and an object in motion continues in motion with the same speed and direction, unless acted upon by an unbalanced force. Okay, better you can write this down, Pute. Newton's first law. What is Newton's first law? Or else you can write it in a point form. What is Newton's first law? An object at rest stays at rest. An object in motion continues in motion unless acted upon by an unbalanced force. This property is called inertia. If you want, I can write this down on the board as well. Anyway, you write this Newton's first law, law of inertia, and write this definition, Pute. Inertia. First point, object is right. Okay, and this is in point form, Pute. This way, I think you can remember. Let me know once you have done, Pute. Write this down on the board. Or anyway, I shared. Okay, let me share my screen again. Anyway, Pute, I have shared a screenshot of this. Okay, what is the first example? First one, carom disc. When you strike a carom disc, it moves. Then slowly stops. Why? This is due to the frictional force. Okay. So it can move longer distance if the friction is reduced. That's why we apply powder to the carom board to reduce the frictional force. Okay. What is the concept here? When you strike a carom disc, it moves forward. But why it is gradually stops? Because due to the friction. Friction is acting opposed to the motion. And second example, passenger in a bus. When let's assume when the bus driver applies the brake suddenly, what will happen to the passenger? Passengers fall forward. Why? When it starts suddenly, passengers fall backward. Why? When the apply brake means Pute, if the bus is moving to this side, to the right side, the driver applies brake to the opposite direction. Okay. When he try to apply the force in opposite direction, still that people in the bus has the velocity of the bus because they still likes to move to the forward side. So suddenly, even if the driver suddenly applies brake, even the bus stops, passengers fall forward because passengers' body doesn't like to stop immediately. What will happen? It's try to move forward and slow down. After that only it stops. Okay, that is inertia. So lower body stops with the bus and upper body keeps moving due to inertia. So that's why our this upper part of the body keeps moving because of this inertia. And third example, okay, when brakes are applied, the body moves forward. Even if the driver applies brake, what will happen? Our body move forward. So seat belt, what is the role of this seat belt? Why we wear these seat belts? Okay, why we fasten the seat belt? It stops the body moving to the front. So this prevents injury. Give me a minute, Pute. Okay. Another small video.
Ever notice that when a moving bus suddenly stops, your body moves forward? Or when a bus starts suddenly, you feel pushed backward? This happens because of inertia. Inertia is the natural tendency of any object to resist a change in its state of motion. If something is at rest, it wants to stay at rest. If something is moving, it wants to keep moving at the same speed. When the bus stops, your feet stop with the bus, but your upper body keeps moving forward. That's inertia in action. This same principle explains why we stumble when someone pulls a chair suddenly. Physics isn't just in textbooks. You experience inertia every single day.
Okay. Then the Newton's second law. Now you know what is from A to Z what is Newton's first law. Isn't it? I hope Anto, Amasha, it's clear. Newton's first law?
Yes, ma'am.
Yes.
Yes, teacher.
Do you want to take a small break? Please go and drink some water and come. Because handovers from 4 p.m. onwards. Please go and drink some water and come. Everyone. Shall I start? Anto, are you there? Amasha? Anto, are you back, Pute? Amasha?
Yes, ma'am.
Okay.
Yes, teacher.
Okay, let's continue then. Now let's talk about Newton's second law. What is this? It's actually tell about the acceleration of the moving object. What is the main point here? Acceleration of the moving object. Acceleration depends on force and mass. That's the in the simple term. Acceleration depends on force and mass. And if we apply more force, it becomes that object can have more acceleration. So more mass means less acceleration. That's the other way around. If we apply same force, more acceleration, more mass, less acceleration, because due to the heaviness, it can't move. What is the formula here? F equals ma. You have to remember this. The acceleration of a body is directly proportional to the unbalanced force and inversely proportional to its mass. Let me show it on the board. Okay. Here, Pute, I think trolley experiment is there. Anyway, let me show you. F is directly proportional to the acceleration of the moving object. Okay. And F is directly proportional to the inverse of the mass. Okay. Which means the other way around. Here. This M is actually constant. Ne? Here M is constant. We can write this like F equals ma. Okay. Let's assume there is a kind of a trolley. There is a pulley and we connect a spring like this. We apply some weight here. First, we apply 1 kilogram. Okay. Then secondly, we apply 2 kilograms. Likewise, we made a table. Weight and the force. Okay. And what will happen? In some point, we can see if we apply 1 kilogram, it started to, sorry, other way around. If we apply 1 kilogram here, we can measure it's like a 2 Newton. Apply this side, okay? Which means this is the force. Okay. Then 2 kilograms means 4 Newton. Likewise, when we increase the force here, the force applied to this direction becomes higher. Let's assume we apply weight on the trolley. Weight on the trolley. First time it's 1 kilogram. Now we apply 2 kilogram of force here, which means it's 4 Newton. Let's assume. When we increase the weight as now 2 kilograms. Now we have to apply again 8 Newton to move this trolley here. Why? When we apply more weight, we have to apply more force to move the object. And what happened to the acceleration of the object? Acceleration with the weight it getting down. With the weight it's getting down. That's why it says force is inversely proportional to the mass. And what will happen? Am I sharing my screen? No. Okay. So this acceleration is depends on the force and the mass. Yes. More force means more acceleration. More mass means less accelerations. Why? Acceleration of a body is directly proportional to the unbalanced force and inversely proportional to its mass. Okay. Let me write one thing on the board. This is the theory F equals ma. Okay. First one, the acceleration of body. Acceleration, if we keep only a this side, what will happen? F divided by m. Okay. And if we keep a here, again F divided by m. Okay. Why I wrote same thing in two sides? Let me explain. Let's assume now we keep the force constant. Here, force is constant. Okay. Let's take it as 10 Newton. Okay. And here we are recording the acceleration with the mass. Okay. First, we are applying 1 kilogram of mass here. Mass means now, if the gravitational acceleration is 10 ms minus 2, the force is what? 1 into 10, it's 10 Newton. Okay. Now let's measure the acceleration here. We take f as constant. A equals f divided by 10 now. Okay. Now we apply 2 kilograms here. The mass of this object, this is the object and this is the surface. The mass is here. Okay. Acceleration is A and applied force is F. Okay. Now we apply or we increase the size of this mass as 2 kilograms. Now what is the force? 1 into 2, 2 into 10. 2 into 10, it's 20 Newton now. What is the force now? Acceleration here. F divided by 20. Now we apply 5 kilograms. What is the force? 5 into 10. Now 50 Newton. Okay. Here F divided by 50. So what is happening when the mass of the object is increasing? What is happening to the acceleration when the mass of the object getting increasing? This side increase. What is happened to the acceleration? Tell me, Anto. Huh? Which one has the highest force? Look at this. F divided by 10. F divided by 20. F divided by 50. Which one has the highest value?
F divided by 50.
In fraction law, Pute, Anto. In
No,
fraction.
ma'am. F divided by 10.
10, yes. This way, Pute. Okay. For example, let's take F as 5. No, let's take F as 50. 50 divided by 10 means it's 5. 50 divided by 20 means it's 2.5. 50 divided by 50 means it's 1. So this way, F divided by, 10 has the highest value. Okay, highest value. May denominator getting increased. If the numerator value is same, denominator getting increased means what? What will happen? The fractional value become decreased. මතක තියාගන්න decreased. Okay? මේ බඩ ලොකු වුණාට ලොකු වෙලා නැහැ පොඩි වෙනවා. ලොකු වෙන පොඩි වෙලා යනවා. Okay? It's become smaller. Okay, Puta? So here when we apply more mass, what will happen to the acceleration? It's getting decreased, not increased, decreased. That's why we call this acceleration is inversely proportional to the mass. You can see here, inverse. Inverse. Understood, Amasha? Stephanie? That's why we call acceleration is inversely proportional to the, this is inverse. Inversely proportional. Here's the proportion mark in mathematics to m. It's 1 over m. Now let's check this side. I'm going to erase this. Now mass is constant. Same object. Now the mass is m for each and everything. But what we are going to do, we apply more forces. First time this much. Second time this much. Third time more force. Likewise, we are increasing the force now. Okay. Let's draw the chart with the acceleration and the force. Okay. Here m is constant. Now we apply 10 Newton with this m. It has, let's take out this m into 10. Sorry. I'll change this way. This is A, this is F. F equals 10 Newton. Okay. So A will become this much value. So let's increase the force as 20 Newton now. Then 20 divided by M, which means 1 over M into, sorry, 20. 50 Newton. 50 divided by M, which is equals to 1 over M into 50. Now you can see this 1 over M is constant. It doesn't change. So what happened to this acceleration? What happened to this acceleration? With the force, we are increasing the force here. Increase. What happened to the acceleration? It's also getting increased. So that's why we call acceleration is directly proportional to F. Directly proportional to F. ඒකත් එක්කම වැඩි වෙනවා. Directly proportional. Directly proportional to F. This is inverse, means 1 over M, like that. And here, directly proportional. So what is the summary? Acceleration is inversely proportional to the mass, which means if the object's mass become heavy, mass become increasing, the accelerations getting low. Okay? Then ඔයා දන්නවනේ, it's hard to push a fat friend than a thin friend නේද? මහත ළමෙත් අල්ලු කරනවට වැඩිය කෙට්ටු ළමෙත් අල්ලු කරන එක ලේසි. Why? Acceleration is inversely proportional to the mass. Now what happened to the force? පොල්ලකින් ගහන එක ලේසි, අතින් තල්ලු කරනවට වැඩිය බෝල් එකටනේ. It's easy to use a club to throw a ball than use our hands to throw a ball. Why? Acceleration is directly proportional to force. Mark is like this. Okay. Better you can write this down if it is clear to you. Let me share a screenshot of this as well. Amasha, did you understand Pute?
Yes.
Okay. Is that boring today or not? Let's do the past papers later, okay? Anto, understood?
Yes, ma'am.
Okay. Shall I continue or do you want more time to write this down?
Ma'am, give me some more time.
Okay. Let me know, Anto, once you have done.
Okay, ma'am.
Still writing?
Yes, ma'am. Give me 2 seconds.
Okay.
Done, ma'am.
Okay. I hope Amasha and Stephanie also done. Sorry. Let me share my screen. Okay, all the summaries here. If it's good if you can write this down, Newton's second law. The acceleration of a body is directly proportional to the unbalanced force and inversely proportional to its mass. I think you already got the fact by drawing this thing on the board. So what is the main formula? F equals ma. Remember that F equals ma, Newton's second law. Okay. When the force increases, acceleration increased. Mass increases, acceleration getting decreases. Okay. Sorry. What is this?
This is your brain when you're struggling to focus. And this is your brain when you're getting in the zone and staying there.
It's a 5-minute video. Here, don't worry about that, Putte. Can you remember in the motion, in the straight line, V minus U divided by T means what? It's acceleration. Okay? MA, we can take out M from this and we can write the expression like V minus U divided by T means what? It's the gradient of the vector time graph, which means it's acceleration. Okay, so same thing. Don't worry about these terms and all. Think and understand. Why that horse can't move now, Anto? Anto? Now a horse can't move. Why? Tell me, Anto. Don't be shy. That horse ate this leaves. Now he is full, huh? His weight getting increased. Okay, now the acceleration getting low, decreased. Now he has to actually he is almost late to meet the king. Now again there is a rock in front of the road, okay? ගල් ගෙඩියකුත් ඇවිල්ලා මැද්දේ තියනවද? යන්න විදියක් නැහැ.
Monster.
Yes. Okay, I think we'll continue this trolley experiment in the next class. I hope you understood everything I have told you today. Any questions? Amasha, Anto, I think Stephanie. Stephanie, are you there? Okay then, Anto. Yeah. Thanks for joining to this class. Okay, so let me end this call. Thank you all. Bye, Anto.
Okay, ma'am. Bye, ma'am.
Bye.